Okay, hello everybody. And yeah, welcome to the last session of the training workshop in Ljubljana. You can already see our last presenter, Andrea, and a robot in her background. So I guess we're going to have a really nice background during the entire presentation. So Andrea is a teaching assistant with our lab, and she basically manages all the tutorials for the courses that I teach. And a big part of that, as discussed during the morning session, is also using robot operating system, or ROS, for doing that. So it's something that we've been using with our students, we've been using with the industry, and basically is the core of Andrea's presentation this afternoon. So with this, Andrea, please go ahead.
Okay, so first challenge is to share my screen. Okay. Okay, and the next thing we will do is start the presentation. Okay, I guess you can hear me well. So I won't be spending so much time presenting myself. I work here for 4 years. I'm a PhD student and also now working as a teaching assistant. I started working with students maybe the last year. However, this school year, I'm on the position of a teaching assistant. So I'm quite new to this field. But the thing I started with regarding work with the students is robot operating system. Otherwise, my PhD topic revolves more around multi-agent systems, and we did also some research on fleet management system, for example, for robots, where we also used ROS. So, but today I will represent ROS as a robotics tool, and I will try to present how we have our tutorials scheduled and what is the content. So to continue, so I will try to present ROS from multiple angles, let's say. In itself, just like you saw today on the first presentation, robotics itself is a very complex field, and also to represent ROS, to present it in a way, in a very comprehensive way, it's quite a challenge because you can do it from multiple views. So today I will try to tell you how ROS came to be, how it was developed up until now, and a little bit what's planned in the future. What were the motivations to create this framework, how it can and should be used, and what are the main concepts that's also connected with how you use it. And at the end, I will try to show some examples that I use when teaching ROS to our students. So ROS is short for Robot Operating System. However, this is not a true operating system in itself. It is more a middleware for robotic systems development, and it is open source, which means that the code is freely available, and anyone working with ROS can modify and reshare the code. You can see ROS as a collection of tools to work with robotic systems, some libraries, and an important part are also conventions that are used when you're programming in ROS. They aim to simplify the task of creating otherwise a very complex and robust robot behavior. and it's intended to be used across a variety of robotic platforms. So the goal is to support core code reuse in robotics research and development, because this is kind of a pain in on this field when you're developing a new robot system or trying to figure out just a part, just let's say a small robotic problem. You need to have the whole complex system, and if you want to do it for research, you have to build this system from scratch. So ROS helps to abstract also the hardware from the software, because we know that robots can be built from various hardware components. And so to make it easier for the code to be transferable from one hardware to another, ROS is also trying to satisfy this condition. So we can see ROS as some kind of process manager, and it offers some tools to use when you are developing your own robotic system, and some capabilities that can be reused from other developers and researchers and engineers. And also an important part in ROS is the ecosystem. This is a network of all the people in the world who are working on developing robot system with ROS. And of course, the benefit is that ROS has a permissive open source license for code reuse. ROS started before year 2007 by a couple of students at Stanford. They were the ones who realized that to research a topic for robotics, you first need to build required hardware and write or rewrite some software for the robot. So the first robot that was that the ROS was intended to be used on was the personal robot PR1. So their mission was to create Linux of robotics. These students who worked also later on this project of the ROS development were Kinan Warbeck and Eric Berger. You can read the story, it's very interesting. So they were students, and they weren't actually the only one who thought of building some kind of framework for robotics development. However, they did realize that to make this framework a success, there's also another component that's missing. So they started gaining funding for their project. So they created a few pitches, and they later managed to convince the one who started Willow Garage, which is a robotics research lab and technology incubator, for some funding. So that's how this this project improved. So in 2009, the first version of ROS was released, and also by supporting the project with sufficient funding, also other engineers, researchers, and leaders joined the project. Two most famous are Brian Gerke and Morgan Quigley. You can still find their works. I mean, they still work and take an overview of this project that is still being developed. So in 2009, they published a paper on a conference and released the first version, and also the ROSCON conference started in 2009. So since then, I mean, they knew that it was important that if you have a framework, that people have to use it. So they tried to convince and invite people to join and work. That was not so hard from one side because it was an open source project, and also on the other side, they had funding for teams who would participate with their projects with working on ROS. So we can see that the number of repositories and packages was growing quite steadily in the years after the funding started. And then the next phase, let's say until now, is continuing development and release also of ROS 2. The development continued under the Open Source Robotics Foundation, which is a spin-off of Willow Garage, which later stopped existing. And Open Robotics renamed itself in 2015 or 17 maybe to Open Robotics. So today, Open Robotics is in charge of the project. It also oversees the development. So how did this next phase start? The OSRF collaborated with NASA on an open source simulation software for robotics challenges, 3 of them. And later they opened also a facility in Singapore and started collaborating with their government. Also, after the first World ROS Conference, local ROS conferences started. That means that we can see that the community is important. So conferences are one way, among others, to keep this community alive and to have a live ecosystem. And with time, as ROS started to mature a little bit, new needs started to be expressed regarding the framework. So in 2017, the new version of ROS was released. So now today, we still have a lot of projects on ROS 1. I still teach for now ROS 1. However, ROS 2 has some advantages, and sooner or later, we will also have to start using ROS 2 also in our faculty, when time allows. So in 2001, there are more than 80,000 developers over the whole world working on ROS, and on GitHub you can find more than 200 packages for ROS. Okay, so to understand the concept of ROS, it's also nice to remember just really basics. A robot is a mechatronic machine, but not just any kind of mechatronic machine, but it's a machine that should sense, think, and act. That means that we expect this machine to be somewhat autonomous from people interaction. It should be able to do some stuff on its own. And the autonomy can only be achieved if the machine is able to sense the environment and then carry computation to make this sufficiently good decisions to perform sufficiently good actions in the real world. So the main concept in robotics that are implemented through ROS is the sensing part, the making decisions, and the performing actions. So if we want to build our own robot system, of course, we first have to start with the hardware. You can use hardware, you can build it from scratch, from very, very simple components, or you can buy hardware that's already prepared to use with ROS. So the one good thing of ROS is that you can abstract the code from the hardware, as we already said. So In this case, in this presentation, I won't be talking that much about hardware. Let's just say that we have some mostly sensing equipment that is has ROS supports, for example, cameras, sensors, more than, for example, single motors. But we do have on the actuation side, we have a lot of robots, complete robots with various degrees of freedom that do have some low-level controllers that can communicate with us. So let's say we build a robot and then we have to program it. So we have to give it the mind to analyze the sensed information and to make decisions, and also to decide how to act and to make those actions in the world. So as we heard, some parts of robotics are already in the late stage of development. So you can buy an off-the-shelf robot, write logic, teach positions, and test the program. That's how a lot of robots operate today in industry. However, this is not the main use case for us. Namely, ROS is a robot software platform that enables us to prepare some I don't know, let's say behaviors in advance before knowing which robot will be using it, because many future robots won't be programmed specifically for each deployment. So in a way, if you buy, you can customize your robot additionally and also easily if you use such a robotic software platform. And of course, it's really good to have an adaptive software to use if you're using it for research. So in robot programming, the most often used languages are C and C++, and Python also sometimes. And ROS can also be used with MATLAB and some other languages. Just to remind ourselves, although you heard also that in the first session, the area of robotics is growing. So there are more and more robots operational in the world each year. So also the projections for the next few years are such that there will be even the number of installations will be growing in the next few years. So developing and programming new robotic systems is definitely an important topic of today's time. So if you want to use ROS, there are not, it's a software platform that shouldn't be, it's not only meant for specific software hardware requirements. So regarding hardware, you need a PC. You can also use ROS to distribute it over various machines. You can also use it on a small computer like a Raspberry Pi. You can install it on a working robot, for example, like Fanuc, or in our case, we have here the Panda robot. You can also include other hardware like sensors and actuators and connect them to the ROS systems. And regarding the operating systems underlying the framework, the most often used is Linux. And it also, it's developed for Linux and tested. However, especially ROS2, and the goal of ROS2 is to be able to run on multiple platforms. In our case, we only use it on Linux. I tried to install it on Windows 2 times and not really successfully. But I didn't really take too much time and go too deep because on my PC I have dual boot, so I use Windows um, for my other work, for writing and stuff, and for robot programming, I use Linux. Maybe it would be interesting to hear from you, because I'm not really sure which operating systems you use in Palestine. Um, so maybe you can also share that with me in the chat. Okay, so there was another thing I wanted. So regarding programming languages, you have libraries for C++ and Python, and also you can use other languages. And what I have written also here is just a reminder to not forget that because if you're using Linux for us, you also need to know some bash commands because we have a lot of command line tools. But maybe more about that later. So what's the general use for us? So there are four main areas. One is to use ROS as a testing environment. So if you want to just, if you have some robots, some hardware, simple hardware, and you want to check some algorithm on it, you can use it as a testing environment. And also it goes is close to the next use case, which is rapid prototyping. So if you're developing some kind of robot, maybe later after you are satisfied with the prototype, you will write more complex software. However, in the beginning, when you're still trying to figure out what works and what doesn't in your prototype, ROS can be used for rapid prototyping. It can be used as a product interface, so you can enable it on your product so you can have a product that is compatible with ROS. For example, you can have a camera that enables this interface for maybe for other use cases, or you can have your entire product that is using ROS by itself, and you can also ship it with robot ROS as a robot operating system, a framework for behavior of your product, especially with ROS2. ROS2, the intention is to make ROS2 even more safe from security point of view, and for to be more useful even in prototyping as in the late stages of the product development. So as I mentioned before, you can create your own hardware. I think you remember from the first session that Rock mentions that we did, in general, he was the one who did most of the prototyping, but we did have quite a few prototypes of small robots that we then used with ROS. And also you can buy finished robots that have interface for ROS, and you can use ROS and program them the way you want. In our lab, we have 3 FANUC robots. The one that you saw Luca working with, is also the one we use with ROS, that has ROS drivers installed. And we also have 2 Turtlebot robots for students that they can work with. Although here you see Turtlebot 3, we have the previous version, but it's the same concept. It enables the students to learn how to work, how to create their own robotic systems. So to maybe emphasize on the importance of ROS, why it's maybe worth learning and working with it. I mean, the use cases are very numerous. Especially, when I was preparing these presentations, I spent quite a lot of time, maybe too much, exploring all the different interesting cases where ROS is used. I decided to present here just, for example, how through the years, if you remember how I explained how ROS was gradually developed up until now. Through the years, also the framework got better, and the goal was to be able to be used also in really real situations. So Terry Fong, who is a director of Intelligent Robotics Group at NASA, had a nice presentation in 2013 where he explained possible uses of ROS. So he said that in space robotics, they have two types of development. They develop prototypes in space also, for example, in the International Space Station, and they prepare the robots for working in space. And also there are really the finished robots that are on the mission, and they need dedicated software to work. So he explained in 2013 that ROS is a good way to become accepted. However, in that stage, it was only used for prototype work, not in flight systems where there are some more stringent requirements. So later, I mean, the first use case of ROS by NASA was to use it with Robonaut, which is a dexterous humanoid robot that was sent to International Space Station. It had a lot of various sensor systems, vision systems, and image recognition systems. So it was used also with ROS in the development phase, and also in the later phases of testing on the International Space Station. ROS was also used with gazebo simulation. As you heard, gazebo is also one of the most important softwares for robot simulation currently, and it's also integrated with ROS. So later, after Robonaut, we have Astrobi, which is a continuation of a project called Spheres. We have spherical cube free-flying robots that can be used in the International Space Station to monitor environment and to use its arm for some simple work, also for manipulation. So also Astrobi was developed with the help of ROS. The next project was well, this is actually not the real implementation by NASA. However, NASA did collaborate by creating this project called Rosject by the construct team that created the gazebo simulation for this robot model. So this is freely available, and you can download it, start it, and try to play with this real robot and simulate its travel over Mars surface. And one of the latest space projects that involves ROS is Viper. This is a mission to explore the south pole of the moon, to explore the contents of water and ice on the South Pole. So here we also have ROS. I mean, in general, this the project and the hardware uses a lot of open source software and also ROS too. And in the future, what we can expect is development of in-space manufacturing and robots repairing satellites and stuff like that. So robotic systems in in space have a very bright future, and they will be very important. So that means that a lot of funding is expected to be provided for development. So one of the next aspects I want to mention here is ROS Industrial, which is, I mean, here we see that, I mean, robots are used in industry, and for the need for advanced usage is still here, although we have off-the-shelf robots doing the same thing over and over again. Sometimes we want robots that are easily adaptable, that can react to changing environments. So a group of companies is connected in a consortium called ROS Industrial, and they developed a framework for industrial manipulators. And the challenge of ROS Industrial is how to transition robotics research and development to the factory floor, so that the robots will be flexible to accomplish a wide variety of automation tasks. But so because it's hard, it's still expensive to program robots for new use cases. So this is trying to make a framework to make this easier. So ROS Industrial, ROS-E, that is taking care of MOVE-IT framework, is an open source project. Its aim is to extend the capabilities of ROS for the case of manufacturing, automation, and robotics. So today you have available a lot of repositories that include interfaces for industrial manipulators, gripper sensors, and device networks. So you can use it and create your own robot systems, just the way that you need it. And also it provides some software libraries for these general concepts in industrial robotics, for example, motion planning, path planning, calibration. So these are tasks in robotic systems that are being repeated over and over again. So here, this framework provides some modules that you can use to develop your system faster. So as I mentioned, the ROS framework was first released in 2009, and after 5 years, after the number of users grew substantially, the needs for some improvements were there. So there were some changes that would have to be made to the ROS framework that could not be made to the existing version. So they decided to rewrite or redo the framework from scratch. So now we have also ROS 2. Its intent is to support multi-robot systems. That means robots that collaborate among themselves. They wanted to make it suitable for final products, not just prototyping. They wanted to make it to be more satisfiable for real-time control and to be able to be used on various platforms and operating systems. So the main goal, the main concepts still remain the same, only in ROS 2 it's desired to spend more time improving just the capabilities and using the tools without needing to spend more time with libraries. That's why the core of ROS was a bit redefined and used some existing standards for data transfer. But what I will now try to explain is what are the main concepts behind ROS. So why is ROS as a framework so strong? What are its cornerstones? So the idea is you want to build some higher level modules for robotics. So when you're using ROS, that means that you're using a certain file system convention. That means that there's a certain way you organize your code, and by organizing it in a special way, in a predefined way, that means that you can also share it with others because they know what is expected. If you share your code with someone, it doesn't have to be remade to be used. So there's a certain file system convention. The next thing is that processes, computation processes are organized modularly, and these tiny models called nodes of a network that is called computation graph, they are loosely coupled and they can exchange data among themselves. And the loose coupling means that you can add or remove a node from this computation graph without major changes in the working of the rest of the graph. And also what comes with ROS is the community. That means that if you're developing something and you get stuck, you have a lot of internet resources like forums, and documentation is very well done. And you also can use work from other researchers. So this is quite a strong point in using ROS. And also, if you have a question that is not yet answered, or if you don't find a solution to a problem already existing on the internet, you can, you know that there is a place where you can ask a question and someone will be able to give you an answer because there's lots of people working with the same framework. So regarding the file systems, we have a code organized in packages. Each package needs to have a package manifest, which is a package XML file, and a CMake list txt file. So that here are the main information about the packages. Then code is organized in various folders in a package. For example, you can create your own messages, services, and your, I don't know, the code that governs the behavior of your process, or node as it is called in ROS, and other stuff. And then you can have multiple packages in one meta package that then you can share either a package or a meta package with other people. So this is the file structure of, for example, you have a workspace folder, which is you have to build the files before you can use it, especially C++ code. So to to build the folder, the CMake compiler is used, and in ROS we use Catkin, which is an extension of CMake. So that's why you need a CMake list txt file. That's a file containing information for building the package to be used on your local machine. So as I mentioned, also the processes, the computation is organized in a computation graph. These are processes that are connected to each other, if needed, of course. So how is this realized in ROS? You have a peer-to-peer network that computes data together. And to do that, you have the concept of nodes. These are processes. They exchange messages over topics. Topics are channels that every node can either publish to or subscribe to. So it can put data to a channel or receive data from a channel. And topics are a simple way of, let's say, a broadcasting way of sharing data, and another way that is enabled are services. This is more synchronous communication between two nodes. We have a concept of master, which is, let's say, it's a mechanism to control the basic working of the node graph, and the parameter server that has a job to serve some general parameters that can be used by any node in the graph. You can also, bags are a simple way to record the working of the computation graph. So any messages sent over a topic can be recorded and replayed later. And when you're replaying this data later, you can use it in different ways. For example, if you have a network where you have one node that is a camera and it collects images, you can record these images in a bag, and later you don't really need this camera anymore, but you only use data that were collected when the bag was recorded. So that means that you record data once and you can reuse it multiple times. That's also useful when you're trying to improve or program some robot system. Okay. Okay. This is the next slide. Let me see if I have anything in the chat. No. So before I was asking you, how many of you are using or familiar with the Linux operating system? One thing that you have to get acquainted with if you're working with ROS on Linux is how the Linux file system works. This is an image I usually show my students because most of them aren't familiar with using Linux. So they use Windows, and there's a little bit different. So you have some C directory partition and then some other folders, and here it's a little bit different. So all the naming conventions across the file systems should be made explicit so that they know what the path, absolute relative path means. That's we spent some time also maybe later returning to this image because it's a good illustration of how you move over this tree of the file system. So this, which is also connected to the next topic, which is if you want to work with ROS, it's good to have at least a basic knowledge of shell commands or bash commands if you're using bash shell. At least the commands for file systems and files management and manipulation. That means to know how you navigate over the file system, which we saw before. You have to know how to set or reset some file permissions, because sometimes you want a file to be executable, and if you don't know how to change the file permissions for a user, you cannot run a file. Sometimes we want to search a few things, and for package management, this is also something, I mean, it's a bit different than in other operating systems. Here you use package manager for installing software or parts of software. So you can, this is also important, or sometimes time consuming, or for the students, or they don't really see the point, but sometimes you have a package missing and you have to install it, and you have to know how to do it. An important also concept that we sometimes with the students struggle to comprehend is the concept of environmental variables. These are variables in a shell terminal that need to be set correctly so that any other program or command you run in this terminal is working correctly. Maybe we'll see that in a few minutes. These are, and also, this is, the title is wrong, actually. It should be ROS command line tools. So the same way that you open a terminal and you use bash or a shell or a bash commands, you also run some ROS tools from the command line. So these are the most often used tools, ROS tools that by me. So there are a few more, but I wanted just to share. For example, to run the ROS system, you use ROS core or ROS launch or ROS run. It depends on if you're starting the system on the master, or if you're starting just a single node, or if you're starting the whole system that is configured in a launch file. And then you have some inspection tools like ROS node and ROS topic, ROS service, ROS SRV, ROS param. These are tools that give you information on the computation graph, on data being sent over the channels called topics in this computation graph. And we also have a few graphical tools that can help, because sometimes if you visualize a thing, you can better understand it. So this is also, I mean, at first sight, it doesn't seem important, but when you think about it, if you want to program a robot system by yourself and you want to know from every aspect what's going on, which processes are running, which data are being sent, which data are being collected, and how to start and stop certain processes, these tools are very useful. So the ROS master is a concept for managing the computation graph. It provides the naming and registration services, like, for example, DNS services for the whole internet. Here we have a ROS master that keeps track of all the processes called nodes, and it can provide them the naming service and registration so that they can find each other and exchange data. It also provides the parameter server that is a collection of variables with certain values and these variables are meant to be accessible to every process in the computation graph. ROS master also starts a process for logging called the ROS out node. This is a node that logs everything to log files so that you can create logs and explore them later after running the system. So this is, for example, how this naming service of the master works. For example, you have a camera and the camera takes images and wants to share it with other processes. The camera is agnostic of who or which process will receive the data. However, it publishes, it tells the master that it will be publishing its data on the topic images. So later, maybe there's a node called image viewer that needs this data from the camera, and it wants to access this channel. It tells the master that it wants to subscribe to this topic, and the master then gives information to this node so that the two nodes are then later connected to each other and exchange data among themselves. So the data later is not exchanged over the master, but directly from one node to another. This is an explanation or visualization of the communication concepts in ROS. So the concept I was previously describing is communication over topics. So you have topics and you have publishers and subscribers, and they share data among themselves. Of course, they have to register with the master first, but then afterwards they exchange data directly. So that is a publish-subscribe mechanism. And then we have another way of communicating, which is of using services. Here, each of the nodes that wants to communicate with another needs a certain object, either a client or a server, service client or a service server. So the service server is the provider of the service, and the client node is the one that is the user of this service. So the client node has to make a request to the server node, which then responds with the calculated response. The difference between services and topics is that transfer of data using topics is asynchronous, whereas exchanging data using services is synchronous. That means that calling a service is a blocking call. When the client node requests a service, it first waits to get the response and then continues with its own behavior. Then some kind of a mix of the both is the concept of actions. This is a mechanism for exchanging data when you want, when for example, the client node wants the server node to do something. However, it doesn't want to be blocked until the action is completed. For example, the movement of robot takes time. So an action client sends a goal to the action server, and the action server is the one that executes the movement. However, while this movement is being executed, the client node can still do whatever it does. For example, it has to analyze some other sensor data while the robot is moving. So here we have a few type of messages or channels for exchange of messages provided. So the client node can send a goal or cancel a goal with the server node, and the server node gives information about the status of this goal, if it's completed, if it's accepted, if it cannot be done, if it is cancelled. And it also sends the feedback, this is not obligatory actually. However, when the action is done, the server sends the result to the client node. You can also, here it's the link where you can research this further. So ROS is meant to work to represent real robots, and robots are very different. So we need a way to represent their shape, their characteristics, their physical characteristics in ROS. So a mechanism to represent a robot in ROS is a URDF format, where you can use simple shapes like box, sphere, or cylinder to describe the shape of the robot, or other files such as, for example, STL files can be used to represent the shape of the robot and the characteristics. So the URDF extension stands for files where we have robot descriptions. We describe each segment of the robot with a link, and each connection between segments with a joint. And we can assign according characteristics to these parameters. So this description is then loaded to the parameter server. So this URDF is a file format which is saved somewhere in the file systems. And after you load this contents of the URDF file, this contents goes to the parameter server, and that's is able to serve this data to any other process that needs the description of the robot. For example, you can visualize the shape of the robot using the RViz tool, which is a tool used for visualization in ROS. Here I have a few tutorial topics that are being that we go through during tutorials. In the beginning, it is usually necessary to make some introduction to Linux, just to bash commands. And also, because we use C++ for programming, we sometimes have to, a year ago, we had to also include some introduction to C++. This year, this was part of another course. So, but still, we did have a problem with a few that unfortunately only listened to the course of robotic systems, but not of the programming course. So they did have some problems. They were not so happy when they had to work with C++. So, these are, I would say, the prerequisite to program your own code for us. So then we start. So, for example, this first part is are some basics before ROS. Then we start the introduction to ROS, and then we explain that what ROS is. For example, the way I tried to explain today. And then we start first by just using the command line tools that are available, and to get acquainted of how to implement the communication examples. So how how do we have two nodes that communicate over a topic or using a service. So here that there's nothing concrete. There's no robotic problem here. We're just getting acquainted with ROS. Then we start discovering how we describe robots in ROS, because here we have the URDF file format, and we also have the Zacro format, which enables then macros for URDF. URDF is actually an extension of an XML, which is a file format used for description. And then we introduce the visualization, the RVs. So how this robot that is described using URDF can be visualized with ROS. And for example, this year we started with industrial robotics, and we used Move It Setup Assistant, because if you want to use or simulate an industrial robot and an industrial manipulator with ROS, some other configuration files are needed. So Move It as a framework also provides a setup assistant where you just take a description of your robot, URDF, and then it helps you create some other configuration files and, for example, controllers for your robot so that you can use it with the Move It framework. So then we get to industrial robot control. We start by moving the robot just from RVs, because RVs is on one hand a tool for visualization. That means we cannot actually interact with the robot. However, the Move It framework provides a plugin where you can use, through RVs, you can set, for example, a goal state for the robot to move to. And then we move the robot using C++ library. And then we also introduce using the simulation. We use Gazebo software, and we then move this robot in the simulation. So we simulate the movement of the robot. And then we continue with the mobile robotics. We use here ROS navigation stack. This is a set of packages meant for robot to use to navigate in a space, to create a map, to use the map for localization and for path planning. So if you're just creating a simple robot from scratch, this can be a nice solution. However, with more complex systems, you might want to write some parts of this navigation stack by yourself. Okay, so we're already past 2. So maybe let's just, I will try to show you a few things we do in our courses. Of course, this is meant to be, these courses are meant to be for, I don't know, 9 to 10 sessions. So I will just be showing a few glimpses. So for example, the first thing we have to get acquainted with is the word and the concept of the terminal. So this is a shell that helps us start our own commands. So to start ROS, you just have to write ROS core, and then some process starts. And for example, in another terminal, you can use a ROS command line tool to see this process. So we can write, for example, ROS node list, and it shows us that there's only one process currently running, because this is ROS core is just a bare minimum that has to start, so that this is the base of the computation graph. We can also then start other nodes. For example, to keep things simple, we have a package that comes with a ROS full installation, which is ROS run. The package name is turtle sim, and then I can see, for example, which nodes are available to run. So let me just run turtle sim node. If I run this node, this means I started another process, and this is a process that has a graphical interface, and it has a turtle in it. So then I open the next terminal, and I use the ROS node tool again. I list all the nodes here, and before it was only ROS out. Now there are two nodes because I started first the ROS core and then the turtle sim node. And another way I could inspect this is by using ROS run, or no, just archit. This will be shorter. Okay, so this is what I meant before when I said that some tools have a graphical interface. So this is kind of the same thing as before. So I can see the nodes that are started, that are part of this ROS node graph, ROS computation graph, and I can see that the two are connected. That means that this is the name of the topic, which is ROS out, and this node sends some messages over this topic to the ROS out node. So I will leave this open for now. And I can start another node. Just so let's say, so here we have a turtle, but the turtle doesn't do anything. However, I can start up a node and ROS run. It's in the same package. I can see that I have, for example, draw square node. This is a node that sends some data to the turtle, and the turtle accepts these messages and starts moving. So if I refresh this graph here, I can see that I have turtle sim, which is the process with the turtle, and then I have the draw square process that sends some data. It's called cmdvel, which is common velocity. So this process sends data on how fast and in which direction the turtle should move, and this is and it receives the location, the pose of the turtle. So I can also inspect what data are being sent over these topics. I can do that, for example, by ROS topic list, and I can see these are all these active topics, and I can, for example, ROS echo. I can echo on a topic. Let's say that we want to see what data are being sent over this topic. So I can now see that this is the data that is being sent in real time. Okay, so this is just so that you get a feeling of what ROS is if you've never heard of it. So the next thing I want to show you, since it's already, the time is already late, I will just quit all for Windows. I'll just say, So one thing we did was, as you already heard, we had a project that with Rosin, and we got financing for execution of a summer school, and we prepared also some course material. So, for example, for industrial robots, in this tutorial we first teach the students how we describe the robot with URDF, and maybe just to show a simple, very simple robot that they create from simple shape is, I will now show you also already the finished version for us. First I have to change to the right directory, and now I have to run the setup script so that that the environmental variables are set so that that Ross can see my workspace and all the packages in the workspace. Now I can run the system from this workspace. This was, let me remind. So this is actually this Fano Cross workspace. You can see the contents. Also, if you're let me just, so this is the so this is the repository that is publicly available. So the repository of this summer school. So here you have, you can also inspect by yourself the contents of this workspace. So we have code organized in packages. So we use the package URDF exercise and the terminals. So I will use the exercise, and then I have to, for example, 2 links. Okay, so here's a simple visualization of a very simple robot. So the concept of URDF is that you have links that are segments of the robot, and then you describe a joint between them and how it can be moved. And here you have, you can control this joint, and you can also, I mean, this is just a visualization with this RVs tool. So this is this introduction to robot description, which is of course just not an accurate model, but just so that we get the feel of how the robot has to be described and how this file looks like. For example, this is this file. So we have an XML file. URDF is an XML type of file, and you have certain tags that you use to describe the parts of the robot. So then next, the same mechanism to describe a robot is used to describe the FANUC robot. So the next thing we do is, after we get the concept of the URDF, I'll just close this. We say, okay, so ROS is meant to be used with any industrial robot, any manipulator. So if you want to use MoveIt, which is a framework for using ROS with industrial manipulation, maybe before I start using MoveIt, I would like just to show the basic, which is this this page. Since ROS is very complex, I often, when I explain ROS, use the concept explanations. So here we have visualized what MoveIt is. So this is a framework for ROS that enables the user to interact with this node called Move Group. That is actually the core of the framework. And this node then has the ability to plan some movement for the robot and to also execute the movement using some controllers. These controllers can be either in simulation or on the real robot. So again, ROS is hardware agnostic. You don't need to really know which hardware is doing the actuation. You just act like you have this robot. It doesn't matter if it's simulated or real robot. And then we have some packages that are part of MoveIt, but are not specific for us. These are like, for example, these are general concepts in industrial robotics. For example, how to plan a trajectory by using planning scene, and how to detect potential collisions with itself, with the other objects. And this is a pipeline to create a trajectory for the robot to move. And here are some other representations of this concept. So we are a user, and you want some ROS process to enable us control of the robot, and also to enable us to use some planning capabilities for the robot. So the next thing we do is, so if we want, for example, to use ROS with this move group, we first have to configure it for our robot that we will be using. So the next thing we do with the students is we run the setup assistant. And that is kind of a wizard that takes us step by step through the configuration that needs data that need to be entered in order for the configuration files to be created. So the result of this process, here we define how our robot looks like. For example, how many links or segments does it have? What are the planning groups that we want to be using the planner with? We also define some predefined poses, like, for example, home pose or zeros pose. And then we also can define some controllers. ROS also has a controller manager process that starts the controllers that will then and that it communicates with the very low-level controllers. We also here define some data that are needed for gazebo, and the result is a package, which is, for example, here, Fanuc MoveIt config. This was the result of this setup assistant. So we start with bare URDF description of a robot, and through this setup assistant, we get some config files that we can use to run the ROS system with. For example, we will run this demo.launch file. We can also see that, I mean, launch files, I don't really have time to explain all the concepts, but launch files are files where we, this is an XML format, where we define which processes we want to start. So the node tag defines a process that the single process needs to be started. We can also include other launch files, so we can create kind of a dependency tree of node files. And so now that I will run the demo.launch file, all the included launch file will also be included and started. Setup bash is needed so that my ROS launch command can access this package. This is conc move it config. This is the package, and the file is demo.launch. So I can see that before, when I was starting the turtle stuff on the turtle node and all the other things, I had to open multiple terminals. Now here I only need to, I can start everything from one terminal. So here I have, this is the ARVIS, the visualization tool. So this robot that is now visualized, here I can use this motion planning plugin to tell the move it node to calculate and execute the movement. So I can just, for example, say plan. And when I click plan, the computation of the trajectory is being carried out, and this is now visualized. If I click plan and execute, the controllers also move the state of the joints. There are some settings, for example, like planned path, loop animation. If I remove the tick here, I can see that this last calculated trajectory is not displayed anymore in the loop. So I can now send the robot to another place. I can say plan, and this is done automatically. So this is the ARVIS tool. It's meant for visualization. So ROS has a process in its computation graph that when we don't have a real robot or even a simulation to provide the data on the state of the robot, so that it just tracks how the robot would move after we, for example, quote unquote, execute this movement. So as we saw before, we can inspect how this computation graph looks like, let's say the backend. We're using the tool RQT graph. And this is it. This is how it looks like currently. So I can see which nodes are running. So I have a move group node. This is the main process for control of this for this robot, and it also provides it receives its data from for example, from ARVIS. So here's the plugin that sends the data, trajectory goal, to the move group, and this node then has to calculate the trajectory. And if I click execute, it has to change the state of the joints. So when the state of the joints change, then also the configuration of the robot changes, right? So that's, and then it returns information on the change of the robots and back to the ARVIS for visualization. Or I mean, we also have a robot state publisher, but I think this is too extensive to be to explain everything in detail. So the main goal for today is to show the general principles and to maybe show you that how we start using, how we teach it, how we teach using ROS, and how it can be used, which are some use cases. Because, for example, the next thing we do then is, if this was just a visualization, we also start with it a simulation, and we can program the movement for the simulated robot. For example, no, I will have now this is another similar setup than before. The difference is that now the information for movement is not just faked by some process in the ROS computation graph, but it is actually simulated in a simulating environment called Gazebo. So if I try to move this robot here, for example, plan and execute, I can see that this robot also moves in the simulation. And I can do the same thing if I connect the FANUC robot that we have in the lab with this ROS system. Then we have to make a connection over the Ethernet cable, and a process to listen for ROS commands has to be started. This is a Carol program on the FANUC. However, when this is actually the only thing that has to be done, we have to set up the correct IPs on both machines. One is the real robot, the controller of the robot in the lab, and the other one is, for example, the my computer, if I'm connecting my computer. So after we set up this connection, I can do just the same, just run this, the similar nodes, with exception of the simulation, right? And send the same commands to the robot, and then the real robot will move. So also that means that also the transfer from simulation to the real hardware is facilitated using ROS because of this compatibility. Okay, so I've been quite long. There's quite a lot of material, so maybe it's time to hear some questions from your side.
Okay, thank you so much, Andrea. So yes, the presentation was about ROS in general, but then as you can see, it's an open source tool. It's something that you can use even without any equipment. So it's a good introductory tool for studying robotics in general. So let's see, are there any questions? Hello. Is there a question?
Hello, thank you very much for your presentation.
Thank you.
Can you hear me?
Yes,
Okay.
I can hear you well.
Okay. Well, actually, the ROS is a very interesting topic, but however, we didn't work in this topic in our laboratory. It will be good for the student to be work in such kind of technology, maybe in master thesis. However, can I share from my side? I need to show you something, maybe related to this topic.
Okay, I can stop share.
On one side. Okay. In our laboratory, actually, we focus on probabilistic robotics. We will use kind of MATLAB, you know. We can sometimes we use SLAM and we make a kind of simulation using MATLAB. So in order to find the position for this, but most of our work here in laboratory and papers related to simulation, because we don't establish an laboratory for robotics. So I read paper related to how to connect rows with MATLAB also. Could you please talk about this issue?
Yeah, so the thing is that we don't really have much experience on using MATLAB because we use ROS and we program what we program in C++.
In C++,
So,
yes.
So, Rok, do you have any other comments on that?
Yeah. So ROS, if you look at it from like a very, very bird's eye kind of perspective, is basically a messaging system between any kinds of programs. So it defines the protocol for messaging as well as the messages that are typically used in robotics. That's the core of ROS. So you have the ROS CPP, which is the C++ library. You have ROSPy, which is the Python library. You also have basically not plugins, but libraries for almost every language you can think of. So there's a library for MATLAB, there's a library for Rust, there's a library for Node.js, so for web applications. Basically, whatever application you have, for example, in MATLAB, you can connect it to ROS just by using this library for messaging and therefore communicating with other already built programs.
And also, if we need to install something in Raspberry Pi 4, for example, it will work. Do you have experience on this?
Yes. So, I mean, we don't really use MATLAB that much. Again, because just we prefer to stay as open source as possible.
Yeah.
But in MATLAB, I mean, just if you Google, and I'm gonna maybe try to do that right now, just ROS and MATLAB, it should be very straightforward to install something. So there's supposedly a ROS toolbox that can connect MATLAB and Simulink to ROS.
Okay. For our student, I can show you also, if you have just can check this. This is can you see this?
We were still seeing the PDF file.
Okay.
Maybe you need to share again.
Okay, this one.
Yeah, we can see this.
Oh, this is a kind of two-wheeling balancing. This is in our laboratory, we built it. We just implement BID controller. We don't go forward in ROS. So after the lecture, I will try to upgrade for the ROS.
I think you can do just the same thing, the very same thing you could do it using ROS, you know? You can use
we have like
ROS.
kind of robust controller to test the stability for it when I apply disturbances. But for ROS, it will be interest, I think.
I mean, the main what the code does can still remain the same. You only use ROS for
Yeah.
how to publish, how to exchange data between processes. So you can
Connect using IP and internet. It will be
yes. You can also use Wi-Fi
Yeah.
to exchange data.
Yeah, typically, if you have a ready-made robot, then you can ROSify it, as they say. You can make it ROS compatible. So the basic interface that every robot needs to provide is what is called a twist message, which is the translational and rotational velocity. And as long as your robot's able to receive this message and actually execute it,
Yeah.
it's immediately ROS compatible, because you can immediately use your keyboard to control the robot, for example. And then if it uses any sensors, you can add those and so on. So you can have existing hardware and just make it ROS compatible.
Okay. Thank you for this.
Okay. Thanks.
Yeah, thank you for the questions. Are there any additional ones, additional questions? Well, if not, then thank you, Andrea, for the presentation. And actually, this concludes the online sessions of the training from University of Ljubljana. We are currently trying to get all the administration together, send you the guarantee letters for those of you who will be traveling to EU later on this year. And I'm very much looking forward to seeing you live here at the beginning of June, probably. So that's going to be, we're going to try and organize a really nice event. So thank you everybody again for attending.
Thank you very much.
And again, thank you, Andrea, for this session.
Thank you.
Thank you. Bye.
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 Bye.